let's say we have a robot here, represented by this kiss, and it's on a football field. Robot's going to move down the football field. I'm going to say how far it moves in certain sets of time, and then we're going to graph that onto this coordinate axis. And this has the x-axis as time, for how much time passes, and the y-axis as the distance that the robot goes. So let's say the robot moves 30 yards in 10 seconds at a constant speed. On our graph, I'm going to say in 10 seconds, okay, 10 is there, it moves 30 yards. So at the end of those 10 seconds, we know it's moved 30 yards, it's going to be right here. Let me say let's have it rest for 10 seconds. So it's going to rest for 10 more seconds. It's not going to move at all. By the time it reaches 20 seconds, it's still going to be at 30 yards. And then let's say it travels the last 70 yards in the last 10 seconds. So it reaches 100 yards at 30 seconds. So 30 seconds, 100 yards would be right there. Now, in this example, the robot is moving at a constant speed whenever it moves. So from 0 to 10 seconds, it moves at a constant speed. That means like at one second it moves 3 yards. At 2 seconds it has moved 6 yards. That's a constant speed, and that's represented by a line like that. From t equals 10 to t equals 20, 10 seconds to 20 seconds, it does not move. So its distance, which is on the y-axis, does not change. And then in the last 10 seconds, it moves all the way to 100 yards. So since it's moving at a constant speed there, from 20 seconds to 30 seconds, then it's a straight line up to 100 yards. So this graph that we just drew is called a distance versus time graph. And x up here, that does not mean x-axis, that just means distance. And distance is in yards because it's a football field. Time is in seconds. So my question, or kind of a big question of calculus, is how fast was the robot moving at any instant in time when it was moving on the football field? So I'll start with an easy one. How fast was the robot moving at 15 seconds? To do that, we would look at our graph. Okay, 15 seconds, the robot was right here at 15 seconds. And to see how fast it's moving, we essentially have to look at the slope of this graph. Because slope, so if I was to take like the slope of any point on this graph, let's get a different color. Slope is what? It's the change in y divided by the change in x. So delta y divided by delta x. So, you know, slope here, you could calculate it, of this line, you could calculate it by taking 0, 0, and then 10, 30, or yeah, 10, 30, and then finding the rate of change from that. But, okay, so for 15, we don't really know how to do that. We don't know how to find the slope at an instant like this. The only way you know how to find slope at this point is to take the average slope. So for example, I could say find the slope of this line in general, and that's what I was just talking about. So m equals delta y over delta x. We could also write that as y2 minus y1 over x2 minus x1. And then for this, we have 2 points. We have 0, 0 and 10, 30. That's this point. And then we could find the slope of this line from that graph. So that's a 30, I'm sorry. So 30 minus 0 over 10 minus 0 equals 3. And since this is actually an application, we're going to need to put units on this. So it's not just 3, it's 3 what's? It's y over x. Change in y over change in x. Y is distance, yards. X is time, seconds. So that'd be 3 yards per second. So at any point on this line, like all these green points I'm drawing, the robot is always moving at 3 yards per second. Okay, if I just asked you now, how fast is the robot moving at 15 seconds, you could probably say, you know, well, what I would do is I do the same process, except I'd use these 2 points. So m equals delta y over delta x, which equals, I'm not going to write that again. It's at 30. This is a point 20, 30, and that's the point 10, 30 still. So 30 minus 30, y1, or y2 minus y1, over 20 minus 10. So that's 0 over 10. That means the slope of this line is 0. That's true, it's a horizontal line. Any horizontal line has a slope of 0. So that means it's moving at 0 yards per second. And then if I ask you to do the last one, which I hope you could do by now, I'll use green again. We'll call these 1, 2, oh, the black pen, 3. So if I was to find M3, the slope of this third portion, M3, that's also delta y over delta x, which equals, this final point is 30 seconds, 100 yards, and the beginning is 20, 30, this point here. So y2 minus y1 over x2 minus x1, that'd be 70 divided by 10, which equals, 70 divided by 10, which equals 7 yards per second. So we just found how fast the robot is moving at different times. Now I'm going to graph that. So I'm going to make a graph of how fast the robot is moving at different times. So I'm going to take, I labeled these points, so I labeled this section 1 as 3 yards per second, this section 2 as 0 yards per second, this section 3 as 7 yards per second. And I'm going to graph those sections. So I'm going to kind of make it on the same scale as I did with this graph. Then 150, you know, oh wait, so I'm going to call this, I'm just going to attach these here, 3, this 0, this 3, this 7. Because the values I'm graphing aren't going to be greater than 7, you know, because 7 yards per second is the fastest speed. So this is still going to be time, but this up here is going to be velocity. And velocity is kind of another term for speed. Just it's what we use in physics. So I'm going to say the velocity. This was 5. So the velocity from 0 to 10 seconds is constant. And we found that it's a constant 3 yards per second. Okay, so 3 yards per second. It's right here. Every instant between 0 seconds to 10 seconds, the robot is moving at 10 yards per second, or 3 yards per second. And then from 10 to 20 seconds, it's moving at 0 yards per second. It's not moving. The speed is 0. And then from 20 to 30, and that's a 20, it's moving at 7 yards per second. So 20 to 30 is 7 yards per second. So by doing this process of finding the slope at different times on this graph and then graphing it down here on a separate graph, we're doing what's called taking the derivative of the distance versus time graph. So taking the derivative is basically just finding the slopes at different instances in time in one graph, and then making it another graph. Okay, and later on we're going to have an equation for a graph, and then we're going to find the derivative to find a new equation. And the new equation just tells us what the slope was on the initial graph that or equation at different times. So I don't know if we'll get to that today, but derivative is just taking instantaneous slopes and then making a new graph or equation out of that. So taking the derivative of this graph, which was just a set of lines, was pretty easy because you knew how to find the slope at every point on here. you don't know how to find the slopes or how to take the derivative of a graph like t, or let's say x equals t squared. So that would be like, imagine the robot moving like this, where it starts very slow and then speeds up, right? That's what the graph of, what's a good piece of paper? Here's one. X equals t squared would look like. And I think I'm actually going to make it 10t squared. Just, it's still a parabola. It's just going to be easier to graph out. So if we have the graph, or we have this function that represents the robot's movement called x equals 10t squared, we're going to take the derivative of this basically. So we're going to find the slopes at different times. So if I follow the same process that we used last time, draw this out. Actually, I think I drew this out already. No, I just made axes for it. If the robot is moving at 10t squared, if I made a t chart for that, so t and x, and then when t equals 1, x is going to equal 10 times 1 squared, which is 10. T equals 2, 10 times 2 squared, which equals 40. And then t equals 3, 10 times 3 squared is 90. So to graph these points, 1, 10, 2, 40, 3, 90. It's going to look like that. And then to actually draw the parabola, it's going to look something like that. So what if the robot followed this motion? Okay. We need to take the derivative of this, we need to find the instantaneous slopes at different times, and then graph them down here. So we can set that up down here. We're going to get 1, 2, 3, and then we want the velocity with respect to time in yards per second. Right, so what we did before is we just took the slope by doing, delta x over delta y. But on this graph, since it isn't a line, we can't do that. We have to use a process, using limits. And I'm going to describe probably in the future more in depth how we actually use the limits, mathematically. I'm just going to kind of explain it in practical terms for now. So